Okay, folks, let's make a start. So we've been talking about semantics over the last few lectures. We talked about word semantics, we talked about verb semantics, we talked about word embeddings as well, and how to be able to derive a continuous representation of words in a big bunch of random floating point numbers. Today we're going to talk about how to be able to get a meaning representation from a natural language utterance. Now, this has got to do with semantic parsing. We're going to parse that a sentence. We're going to identify the verb, the noun phrases, the relationship between the verbs and the noun phrases, and from that be able to build something in our meaning representation language. Our meaning representation language we talked about before is going to be some sort of logic, some sort of first order predicate logic, probably, possibly with some conditions on it. Okay. So, you know, we've been gradually moving up and like saving to today to talking about how to get meaning from natural language utterances, although we've touched on a number of these things as we've been going through, but we're going to particularly talk about semantic parsers today and actual techniques and, you know, whether they're any good. Are they useful? Do they actually do things? Okay. Now, we've already identified some of the things we're supposed to care about in a meaning representation language, and I'd like to, again, focus on them a little bit. So the sorts of things we'd like to be able to do, and we can't do everything. We're not going to really understand abstract contents from sentences, so they've got to be pretty explicitly meaningful, literal meanings, okay? And although we might be able to capture some surface word things with various techniques, we're really talking about at the moment is how to get representations of sentences that have real content that can be represented in a reasonable knowledge base. Okay, so we're sort of going to ignore some of the poetry type things, and we're actually cared about these hardcore factual things about where X was born and when they died, what are they famous for, what movies did they appear in, things which have very literal meaning, because that's what works. We like to do the other stuff, but it's sort of too hard at the moment, and we don't really have good ways of even evaluating it, even if we could do it. So we can think about things like maybe grading assignments, especially assignments that have very clear answers. So if you think about an assignment that asks a very specific question about something that was in a passage, and then you want to try to do the question answer things, like sort of what you've been doing for the projects. You have been doing things for the projects, haven't you? Because that's important. Maybe understanding what a menu is in the restaurant, so you can ask queries. So given the menu, can you extract all the information about the names of all the dishes, the descriptions of all the dishes, whether it's vegetarian, whether it's spicy, whether it's gluten-free, whether it tastes nice, all of these things that you could extract from a menu, at least a human could if they were trying to type it into an SQL database. Can you actually do that automatically from the menu? And maybe even following a set of instructions. In fact, that's think about what a programming language is. A programming language is some high-level textual representation that has a very concrete meaning, which you can then execute on the machine and get the result out of it. And you could think about instructions on how to do something could be the same way, but in natural language. They might be instructions about navigation, about how to get from here to Starbucks. They might be information about how to change a wheel on a bicycle. They might be instructions about how to take over the world, okay? Although I think there might be quite a long number of that, or the requirements could be too hard. So we're talking about the literal end of the language. We're not talking about the philosophical end of the language, because we sort of can't do that yet. We're still talking about symbolic representations of forms. We're not talking about continuous representations, and continuous as in a big bunch of floating point numbers, like some latent space in a neural net. And actually, everybody agrees that the latent space of the neural net is not going to capture particularly complex meaning things. They'll represent some of that, but not all of that. And we are specifically interested in the sentences that do have a good symbolic representation. So we're pre-selecting the sentences or the domain for something where that makes sense, okay? We're probably talking about something that's a meaning of a sentence and one sentence and as one representation. We're probably saying we're going to ignore about a lot of the natural language ambiguity that's there. And we're probably talking about sentences that are discussing the real world. Now, one could imagine you could have a bunch of natural language stuff that described a video game. And as we all know, that's the real world too, although some people might argue that it's not. But we're talking about that it has some, actually is the technical term of denotation. So the description that we have is referring to something else that's real. Even if it might be a virtual world, it's still real in the sense that we are describing that. We're going to focus on first order predicate logic. It's the easiest one to focus on. It has many of the properties that we'd like of a meaning representation language. Almost every implementation that deals with first order predicate logic actually isn't first order predicate logic. They make some assumptions about the world which actually break the true mathematical definition of it, but they're reasonable assumptions to actually do. So there's certain constraints about how variables are actually dealt with. For example, it's a very classic thing that people will do in meaning representation languages. Also, first order predicate logic doesn't actually have a good way of representing questions, okay? At least not within first order predicate logic, but you often would like to be able to ask the question, is this statement true? Because that's a lot of what we're actually doing. If you remember before, we were talking about a paper bag that had a whole bunch of facts in it, and we're trying to find out whether our fact is in that paper bag or is derivable by the facts that are in the paper bag. Actually, first order predicate logic doesn't talk about how to do questions. So you have to have some meta level, and it's perfectly reasonable and it can be well defined, but you know, a logician would point out, it's not first order predicate logic, it's something else. But it's something else that is a logic and can be fully defined. We talked about these things before, but I'd like to highlight them because it's the sort of question that one might get asked if one was doing, for example, an exam, or much more importantly, it's the sort of question you should ask when someone comes along and says, here's my wonderful representation that covers everything in meaning. You should be able to ask the questions, does it actually do X, Y, Z? So you should be able to ask that because it makes you look intelligent, makes you look knowledgeable, which is more important than the exam, actually. We'd like to be able to deal with queries. So we've got a bunch of facts or a bunch of, you know, meta facts that say about all X or Y. Can we actually derive answers from, do CMU students follow politics? So we'd like to know whether that's the case. So it means we have to have a representation of CMU students. We have to have representation of politics. We'd have the representation of what it means to follow. I mean, maybe it's just follow politics, CMU students, and that's fine as long as you can actually identify that. We'd like to not care about ambiguity. We like to choose one case, and maybe there's a few cases that we'd like to deal with, but we'd not like to deal with the overall ambiguous things that natural language actually has. So if we take a sentence like, CMU students enjoy visiting senators, it is ambiguous, okay? It could be that the students are going to the senators and visiting them, or it could be the senators are visiting. Okay, and visiting is being used as an adjective in this case. It has two meanings. And you might go, oh, no, it doesn't. No, it really does have two meanings. And different circumstances with almost exactly the same syntax you will think of one of the meanings or the other meaning. Okay, now it's okay in a natural language system to say, I only care about the meaning I get. I'm not going to care about the other meanings because that isn't important to me. That's absolutely fine. And actually, that's almost always what people actually do, because actually really only one of the meanings is reasonable. And even if the other meaning is reasonable, it's okay that you don't get it as long as there's some other way to actually do that. I'd like to deal with some aspect about vagueness. Okay, so if we hear Sally heard the news, do we actually have to know what the news is? Or can we actually have a representation of the news that's ambiguous, or at least not fully defined with respect to what that fact is that's the actual news? We'd like to be able to cope with ways of expressing the same meaning in different forms. So this is like, we'd like to get a canonical form no matter what the surface level of the sentence is. So the candidate evaded the question and the question was evaded by the candidate. They mean the same thing. Now, there's some pragmatic thing that's different about those. The focus is different between these sentences, but you know, for most part of what we're dealing with in natural language processing, we'd like the first order predicate logic representation of these two sentences to be exactly the same, okay? And sometimes it won't be as simple as that, merely passivization. There might be slightly more complex ways of actually describing the same thing. So some words are going to map down to the same thing, even though the surface level is different. We'd like to be able to draw conclusions for things. So given a knowledge base and given information about things in that knowledge base and be able to generalize from the examples, we like to derive information, okay? Who could become the 48th president of the United States? That's the question we're all asking today. Actually, it's not 47. We're only at, oh yes, it is 48. That's the big question, actually. And actually, we might not know the answer today because if it's Biden, we do. And if it's not Biden, he's not the Trump is not the 48th. It's the next one after Trump. This is really focusing on the point that when we get a representation, okay, it really should care about our domain. To get a representation that deals with everything in the world, okay, is an admirable goal, but I think realistically a waste of time because actually you're never interested in representing everything. You've always got a particular application. And even when somebody tells you, no, it must represent everything, the answer is no, it should represent the things that you actually care about. If you're building a system about movies and dealing with queries about movies and collecting information about movies, it should know about movies, directors, actors, plots, musicians, locations, things that are in IMDb, actually, in particular, and it shouldn't have to care about chairs and tables and forks and spoons and how spicy the food is, probably, okay? But you will define what that space is, and you want a meaning representation and a conversion process that maximizes for your domain, okay? And ignores the other things, and that's absolutely fine, okay? Even though somebody will come along and say, oh, but you can't represent that. If they don't accept the answer, yeah, you're right. Just say, we'll work on that tomorrow, okay? But that's, you know, tomorrow, tomorrow, tomorrow. There's a whole bunch of aspects in philosophy, logic, mathematics. It's in that square of research that actually gives very detailed definitions and discussions about definitions about what it means to be a logic, okay? This is often called model theoretic semantics. So what we're talking about is we're going to have this string of symbols, okay? Let's pretend that they're just simply ASCII symbols that are the symbols, brackets, the ands and the ors, in our first order predicate logic, and we're going to give it meaning. We're going to define every single symbol that is in there and talk about it in terms of an actual thing. So it's going to be a model of some actual thing. Now that actual thing might be an SQL database, or it might be, you know, everybody in Hollywood, okay, not the town, but the notional movie domain, okay? Or it could be, you know, all the robots in the room that you actually care about, or it could be all the people in the building that you're working in, but it's going to have a real thing, and you're trying to have a model that's representing that real thing, okay? And each element that you have in your representation will denote, so if I have this thing, it will denote a particular thing in your world that you're trying to describe, okay? I remember the particular example that was in one of the books I read years ago. They said, this is showing how old the book was. I wasn't reading it at the time. They said, if I have a representation of Richard Nixon and I want the meaning of Richard Nixon, I have to have a function, which I can apply to the ASCII string, Richard Nixon, that will give you actually Richard Nixon, okay? And I would like to point out that Python does not have a library for doing that yet, because I'm pretty sure Richard Nixon would be pretty surprised if somebody ran it and they ran the function on the symbol for Richard Nixon and Richard Nixon appeared. Considering he's dead, it would be pretty weird. But that's what we mean by the meaning, okay? And so we can't have a computational thing to do that, but we can have a definition, okay? That mapping from your symbolic units that you have in your calculus or logic, the things that are in these expressions, to the world that you're talking about is called an interpretation. And there can be different interpretations depending on certain definitions. So we could swap out a particular world and put in another one. And sometimes you want to do that if you're talking about particular customers or you're talking about particular products, you might be swapping out that particular product and putting in another one. And these expressions now mean something. You've changed the interpretation, okay? But you've done that in a mathematical sense, okay? Now, there's non-trivial, very accurate definitions for all of these things. I'm only glossing over, but be aware that all these terms actually really mean something and people complain about it if you don't get it right. I don't. So here's a particular model. So the domain is a bunch of people and restaurants and food genres, okay? Genre is not the right word. Cuisines is the word I'm looking for. There's a bunch of properties, okay, about these that are relating these objects, these entities together, okay? There's a bunch of relations, okay? So the properties have got one argument. So, so in other words, the restaurants, Green Mango and Udipi, are crowded and Casbah is expensive, okay? There are relations where it can have multiple arguments. So likes, we can take Karen and Green Mango. Likes can take Frederick and Casbah, etc. So we've got these facts. These are the things that go in our paper bag, our knowledge, okay? We've got these symbols that are going to represent these, and we've got the information. So we've said that there are names of properties. We actually have to say, well, who's got those properties? So crowded, G and U, expensive has got C, likes, and it gives pairs of who likes who. And what we would say is that the meaning of the word Noah, okay, within our domain is N, okay, which that's not as interesting as actually having a physical human called Noah, but he was busy, so he couldn't come in today. But there's this syntactic representation, and the semantic representation is the denotation of these objects into your model, okay? So let's look at some English examples. So Karen likes Green Mango and Frederick likes Casbah. Can we get a first order predicate logic representation of that? And the answer is yes, we can do that. We'd like to be able to represent these statements in a way that lets us compare them. So we want this first order form. We want to be able to have whatever that form is that can do what's called truth conditional semantics, which basically means given that statement that we have from the sentence, we can evaluate, interpret whether that is true or not true, okay? We could say, here's basic facts about the world. We could convert them, and then we could say they're all true, and we put them in the database. And then we could talk about queries with respect to that. And it depends on what you're actually doing or the stage that you're doing on building things, okay? Terms refer to actual elements in the domain. So we have a symbol that's a term, okay? And we have constants, because we might want to have constants. We can have functions and variables. You'd be familiar about these type of things in programming languages. So Noah would be a term, and spouse of Karen, oh, I now know who the Noah probably is. And we could have variables as well. They'll often be X, Y, Z. Or they might be in italic, or you just have to work them out, and it's not always obvious, sorry. Predicates are things which can refer to sets and relations. So we can say serves Casbah Mediterranean because it gives Mediterranean food. And we can have logical connectives like and, or, not, and implies, okay? Now, implies is actually exactly the equivalent of a or not a, but so you can actually replace implies with some other logical form and it means exactly the same, but we often use implies because we like to do it. And we have quantifiers. Quantifiers are probably the things you're less familiar with. Quantifiers in first order predicate logic, for every variable that's introduced, there must be a quantifier that that variable is within the scope of. Okay, so again, if you got used to programming languages, you're usually aware of what the scope of a variable actually is, and you should know from C++ it's the thing that it's not. This is not in scope. Sorry, C++ usually tells you that. So you could think about within a function in a programming language, the variable that appears at the top is within scope within that function. And that's what we mean. A quantifier is a thing that actually says this variable is now in scope everything within the sub-expression that follows that form. And quantifiers can vary from, well, in first order predicate logic, there's actually 2 ways to do this. One is what's called existential, which makes it sound posh, but it's just an upside down E or a backwards E, depending how you look at it. It's often read as there exists. While the other one is universal, which is an upside down A, which is usually read as for all. So there exists is the wrong E and for all is the wrong A. The meaning of those means that if you've got there exists X, it means that this statement, okay, there has to be one way to make it true. If I bind the variable in there to some object in my domain and it makes it true, then it's true. Now, I could bind it to every object in the domain and all of them are true and it's still just true. There just has to be one, at least one, okay? Well, for all, okay, it basically says every object in my domain can be given to that variable name, and then the statement is still true if it's true, or it's false if it's not true for every single value that the variable can get. Now, there often isn't an explicit type system. Definitely in first order predicate logic, there's no explicit type system. And therefore, when you really say for all, you mean absolutely everything. Although usually the body has got some constraints on it that allow you to be able to restrict the domain of that variable, wrong word, a confusable word, restrict the things that you're really going to match for it to be true, okay? A restaurant near CMU that serves Indian food, okay, that could be written as there exists X such that it's a restaurant X, X is restaurant, it's near CMU, and it serves Indian, okay? And that we find comma here between the restaurant and near is going to be the and form. All expensive restaurants are far from campus. So what we could say is, for all X, if it's a restaurant, okay, and it's expensive, it implies it's not near CMU, okay? So we can get representations of sentences like that. Now, they are not the same sort of sentence that you might get in the newspaper, but they might be something that describes in a database or gives you facts. And in fact, often the first paragraph of the Wikipedia entry about people is very much like this person was born in so-and-so, their parents were so-and-so, and therefore it's giving very factual information, which for the most part could be converted into first order predicate logic. In fact, there's tasks that we actually do in challenges in research that will try to take first paragraph of Wikipedia for bios. It doesn't work for everything, but it works for some class of things in Wikipedia. See if we can generate facts out of them, database facts out of them, which are effectively first order predicate logic representations. I'm going to add another thing on top of first order predicate logic, which is often used. It's called lambda notation. Again, if you've done programming languages, this will be somewhat familiar to you. If you've done logic, this will be familiar to you. And if you've not done any of these, well, I'm going to tell you about it now, okay? It's a way of making anonymous functions. That's really from the programming language point of view. It's a way of basically talking about something before you know about the something. And it really is a bit like, you know, a programming language function. Lambda X basically means the next thing that I'm talking about, the next expression I'm talking about, okay? This is an abstraction over some set of first order predicate logic examples. And if you sometime tell me what X would be, and you replace the variable X everywhere within this form, and then execute it, find out whether it's true, then that is fine and it's going to be valid. The argument, the second part of it, is the body of the function, or it's going to be a first order predicate logic statement, can have ands and ors in it, and have other lambdas in it as well. That's absolutely fine. It allows us to be able to talk about a partial representation or an abstraction of a first order predicate form without having to make it non-conforming to first order predicate logic. Okay, so for example, we can talk about lambda x near x CMU, and what we're saying is this is a representation of something, okay, that could be near CMU or not, but we don't know what that something is, and we know other properties of it yet, but we'd like to have a representation of it. Okay, likewise, we can have multiple lambdas, and they can either be in series or you could think about them together, and it sort of depends. It's just fine when they're in series, although sometimes you want to change the order of them, but most of the time what we're talking about, we don't really have to do that. Lambda reduction means if you've got a statement and you've got a value, okay, means actually reducing this lambda expression by taking this value and taking whatever that lambda x is and replacing x with whatever that value is, okay? Lambda x something with some value afterwards means exactly the same as actually applying it and removing the lambda. So in other words, lambda x near x CMU applied to Lulu's noodles means exactly the same as near Lulu's noodles CMU, okay? Now, again, it's a subtle thing, okay? You have to understand that 2 plus 2 actually means the same as 4, okay? The surface level representations are different, but when you apply the plus function to the two arguments, the 2 and the 2, and actually calculate the value, you get this value 4, which the ASCII value 4 has the same interpretation, the same denotation in the real world, assuming that 4 is an abstract concept which actually exists in the real world without you having to write it down. That's a deep philosophical question, which I'm not going to answer because it doesn't need one. Well, it doesn't need one here. So lambda reduction, okay, is just taking this lambda expression and applying it. Think about it as simple as that. In some classes, in fact, in some programming classes, you would actually be given that as a homework assignment, and you have to be a little careful about making sure that the X remains as a unique name, because if the expression that you're applying to, in this case it's simple, it's Lulu's noodles, but if that was a lambda expression that had an X in it, you have to be careful not to mix up the X's because they're actually different X's. Inference. So one of the advantages of first order predicate logic is you can infer things from it, okay? And when we say inference, we don't just mean we can make shit up. What I actually mean is there is a formal logical set of rules that you can prove to be true and use to try to prove things from your database of information, okay? So it's a very, very formal definition of the notion of inference. So if I have in my data some statement, alpha, and some other statement that says alpha implies beta, okay, and I know that alpha is true, and I know that alpha implies beta is true, then I know that beta is also true, okay? This is called modus ponens, okay? It's called forward chaining as well. It's a standard form of inference that works in logic, and particularly for order predicate logic, but also in lots of other logics. Boolean logic, if we go simpler, or further up the scale. Backward chaining, okay, is take a query beta, and it looks for propositions like alpha and alpha implies beta, okay, that would prove beta. So if you ask the question, is beta true, some first order predicate logic, and it's not in your database directly, but there's something that says alpha implies beta, you then go, oh, right, okay, so if I can prove alpha, I will know that beta is actually true. This is what's called it's not quite the same as abduction, but it's almost the same as that. It's not assuming it's true and therefore implying that alpha has to be true, which is what abduction would actually be. This form of proving is actually the fundamental execution form for the programming language Prolog. Every year when I give this lecture, I ask the embarrassing question to the people in the audience if they've ever used Prolog, and people rather embarrassingly raise their hands. I can't actually see whether the hands are raised, so you can raise your hands if you want. But the concept of what's in Prolog is actually still used in lots of different theorem proving techniques. There was a programming language, in fact, there still is a programming language, which led the AI revolution in mumble year, maybe the 80s, maybe even earlier than the 80s. But its form of execution was fundamental backwards chaining. These form of theorem proving, these form of inference are both sound. That's a technical sense of sound, which means that everything that is true in the domain of all of the axioms, all of the alpha betas that you have, and alpha implies beta that you have, that that can be proven by those are in fact true. So it doesn't actually make errors in what it proves. However, it does not cover everything that is actually true given these forms. Now, the logicians actually care about the space of things that are provable and the things which are actually externally true that can or cannot be proven from the examples that you actually have, so-called sound incomplete. This is equivalent to, caring about programming languages being Turing complete. The holding problem is a non-trivial problem in computer science, but even though in general we can't tell whether a program actually is going to stop or not, in actual fact most of the time we can tell, and if we don't, we control C it, and so that it dies anyway, and most of the useful programs stop. In the same way that most of the useful things that we can prove, and therefore it's not really a problem. It means that there's something wrong in the sense of there could be other things that could be true that we can't get, but we're not going to care about those. So the soundness and completeness is something that's mathematically there, but it's not something that is really going to affect us when we're actually using first order predicate logic. There's a chapter in the book, I don't know which version that is, and I know when we put chapters references in the book, they don't always get updated. So there's a chapter in the book that talks about meaning representation languages. In some version of the book, it might be chapter 17, okay? And representing events and states in first order predicate logic, dealing with optional arguments, and that's something that we're going to have to deal with because natural language is like this. So sometimes we have I eat, versus I eat a pizza, and therefore there's optional forms. Something like representing time is surprisingly hard. We've been trying to do that for thousands of years, actually genuinely thousands of years in logic. And getting a good representation of time is surprisingly hard. We probably want to introduce the notion of an event timing and then put a structure in the order of the event timing, and then we're going to attach our information to those particular event times. And you have to understand that sometimes the facts are very confusable, okay? Who is the president of the United States, okay? And the moment at this very moment really is Donald Trump, okay? It doesn't matter about the election because Donald Trump is going to be president of the United States until January 20 something. I can't actually remember, okay? Unless something happens. If he dies, he won't be, okay? If he resigns, he won't be, okay? Both of these are pretty unlikely, but it doesn't matter who wins the election. There will be, President Trump will actually be there. Now, he won't be the president forever, okay? Guaranteed, okay, that he won't be the president forever. So we have to have a starting and an unspecified ending point for him being the president of the United States. Likewise, my great-grandfather said to my great-grandfather, my grandfather, who is the president of the United States, okay? And it wasn't President Trump. Both my grandfather and great-grandfather have long since passed away, and I'd really have to think about that, of who might be the president, but it's, you know, Eisenhower or maybe earlier, not very sure. Okay, so you have to care about the time that the question was actually asked in order to give the definition. Okay, so which makes things interesting, and sometimes you want to do it, and sometimes you're in a constrained enough environment that you really can do that quite well and quite interestingly well. There are also non-first order predicate, first order logic representations of meaning, okay? And sometimes they're more complex than first order predicate logic, and sometimes they're simpler. But they're usually targeted towards the particular task that you want to do, okay? And it's a good idea to think about it. In fact, it's always a good idea to think about, here's our representation of what the meaning actually is, and let's try to work out whether it's like first order predicate logic or not. So for example, most dialogue systems, let's actually be more, almost all task-oriented dialogue systems, which apart from a few toy examples that exist in the world, so things like Siri, things like Alexa, what they actually do when they get the natural language form is they get a representation of the particular statement that the person said, the string of words that the person said. They usually label it as what's called an intent. Okay, at least that's what Alexa called them. I don't know what the internal form and Siri is called, but they'll all recognize the term intent, and they'll recognize the slots. Now, the intent is effectively a predicate, and the slots are effectively the arguments to the predicate. Okay, some of them may be optional, but they'll get this representation. They may not call that first order predicate logic, but it is a meaning representation. And of all the possible ways of asking for the weather, they'll get the same representation of, this means ask about weather in Pittsburgh, or if that's what you're actually saying. So what's the weather like in Pittsburgh? Is it raining again in Pittsburgh? Do I need an umbrella to go home? All of these ways are really asking the same question, and therefore we get a canonical representation of that, that it can then be executed in the great Amazon cloud to be able to give the information of course it's raining. Actually, I don't think it is raining today, so it's quite nice. First order predicate logic has been around for a very long time. Okay, that's the first thing. It's been around for, at least in its current form, for hundreds of years, but things like it have been around for thousands. In the computational world, using computers in the form of natural language processing, from about the 90s to the 2000s, it sort of became less interesting. In the 80s, there were groups of people who were trying to convert natural language to first order predicate logic, and they sort of gave up, although there is this company called Sci-Corp that's managed to stay in business, usually by aiming for a particular domain, say medical or legal, and come up with a first order representation of information about medicine or information about laws. What people noticed, though, as we got into the 2000s, when we started getting very large online, very full of knowledge information, particularly Wikipedia, okay? Although IMDb was a good example of that, and it's been around since the 90s, that people realized maybe we should start actually trying to go back to get representations of this nice, well-written text that has literal facts in it, because that's what Wikipedia is mostly about. I'm pretty sure there's things that are not things in the real world, like I'm pretty sure there is an entry for the unicorn. Sorry, I was going to use the unicorn. I have to admit that the national animal for Scotland, my home country, is the unicorn, which is a little questionable, but hey, we do have the Loch Ness Monster as well, so maybe that's just fine. But although there are things in Wikipedia that are fictional, and if you don't believe that unicorns are fictional, there's an entry for Sherlock Holmes, and Sherlock Holmes is unquestionably fictional, even though we can apply properties, but it's literal facts that are in there. And the question is, could you take Wikipedia, use NLP techniques, and end up with facts coming out of them? Now, what people actually started doing was they said, well, actually, we don't want the natural language processing. We want the facts because it's going to be easier for us to be able to answer questions. And so people started doing it by hand, okay? they're wonderful. I really appreciate that these people do that, because that means we get training data. And now we have training data where we have a bunch of Wikipedia entries and a bunch of first order predicate logic facts. They're actually not first order predicate facts, but they're almost first order predicate facts. And so we can actually use them. So things like Freebase or WikiDB are things which have got the relationship between a particular piece of text and actual facts that come out of it. And sometimes you have to align these properly, and sometimes they get out of date with each other, but for training data, it's pretty good, okay? And there's lots of other things. In fact, if you look at various pieces of research over the years, trying to ask complex questions, tell me all the states in the US where the capitals are close to a river, but are bounded by at least 3 states that are not on the coast. That particular sentence would actually work in a bunch of research that happened way back from the 1980s to now, actually. And there are people who were working on dealing with those types of questions. And they're really along the lines of, can I take natural language and convert it to effectively SQL queries, which is very useful for people who wish to ask questions for a company database that's got products or people in it, because it's easier for them to ask the questions in natural language, even though it's a semi-formal language that they're using. There's a project here at CMU called Read the Web, which has been trying to extract facts from natural language, including Wikipedia and news stories, and trying to learn general things that baseball players are also in teams, okay? Because all the examples of baseball players are in teams. The particular teams are in particular cities, okay? So that the Pirates are in Pittsburgh, okay? So let's try to connect the aspect of syntax to semantics. So what we'd like to be able to do is take a sentence and convert it into machine readable language. Let's first order predicate logic, okay? We're going to assume everything is extremely literal. We're going to assume that, you know, names just mean that. There's no other interpretation. We're going to make it as simple as possible and see if we could actually do it. This is called semantic parsing. It's a subject. People do PhDs in it. In fact, I'll even refer to some of the PhDs that have come out of CMU in this space. There is an assumption of what's called compositionality. And in compositionality, what we assume is the meaning comes out of combining its subparts, composing the subparts. So we're assuming that the meaning of the sentence, John loves Mary, can be derived from the fact that it has John loves and Mary in it. Not all sentences in English are like that. Not all sentences in any language are like that. In fact, not all words have a compositional meaning. The word hot dog has got nothing to do with, well, probably nothing to do with hot and nothing to do with dogs. It is a sausage, okay? The word straw man is almost never used to mean a man made of straw. It usually means it's a rhetorical thing in an argument. And New York is not a New York. York, I assume, is a city in northern England, though it's also near Toronto. But I think it's the one in England that it was named after. And therefore, some things just don't have a compositional meaning. They together just mean the real thing, and so we have to take that into account. But the big idea is really what we'd like to be able to do is, given a sentence, given the parse tree, we're probably going to use these Lambda expressions that we've been talking about, and we're going to take these Lambda expressions and sort of assign them to different bits and maybe write rules for the syntax. Each of the syntax rules has a standardized rule that when we evaluate things, we end up with a statement at the end, okay? So here's a sentence: Noah likes expensive restaurants. Here's the parse tree above it, and we would like to get out of this the first order predicate statement for all X, restaurant X, expensive X implies Noah likes X, okay? And that's a perfectly reasonable meaning out of that sentence, Noah likes expensive restaurants. So how would we go about doing that? Okay, so first what we'd like to do is look at the terminal symbols on this tree and actually try to assign some sort of semantic representation, partial semantic representation. We're going to talk about the word Noah, just the word Noah. Isolated from all of this sentence, we'd like to get a representation of it. And so what we can do in the square brackets, okay, is actually give its semantics. No, it's quite easy. It's a proper name. We're actually talking about a particular person in a domain who has a symbolic name, and therefore we can just call him Noah. Okay, so that's okay. Let's have a look at the word likes. So likes is a verb that takes two arguments. Okay, it takes something likes y, x likes y. Okay, and if you just look at the word likes as a verb in isolation from this sentence, we want a representation that's got the two arguments, but we don't know what the two arguments are yet. They're going to be given to us while we're actually doing parsing. So what we can say is, we could say the representation of likes is actually a lambda expression, a lambda expression that's got a function, okay, that something is implied to likes, and a lambda y and a lambda x, okay? And so these are the variables that we're going to put in there. So we've got actually a condition. If this condition is true, y likes x. What does expensive mean? Well, expensive is going to be sorry, it keeps going forward for me. Expensive is a predicate that takes an argument. We don't know what we're talking about in terms of expensive, but in our database, we're going to have a list of the things that are expensive, and they're going to have the property expensive thing, okay? And so we can do lambda x expensive x, and likewise restaurant can be lambda x restaurant x, okay? And so these are, and I selected these deliberately because I know they're going to work, okay? And we'll come to that in a minute about how do we find these things for arbitrary new words. But these are abstract representations of these words which are independent of this particular sentence. They're still the right meaning for this sentence, so there might be multiple entries for some of these words. So likes could also be a noun, okay? As in, how many likes did you get after you made that post last night? Okay, and that's a noun, but we're not talking about that noun, we're talking about the verb case, okay? So we can assign all of these to each of the fruit of the tree. Then we can look at all of the rules that we have, and yes, I mean rules. They may be derived automatically from something, but I'm talking about for each of the syntactic rules, we can give a definition about what the semantic part of that rule is. So if we have over here on the left-hand side, NP goes to NNP, okay, so there's a full noun phrase, and this is to a proper noun, we can just say, well, if we have got this rule, the semantics of the NP is just the semantics of the NNP. That's easy, that's gonna be the Noah one, okay? Likewise, we're gonna have other forms of NP where we have an adjective, okay, and we have some other noun, okay? What we can do is we can say, well, the semantics of this is whatever the representation abstracted from the adjectival form and whatever the representation, the semantics of the NNS actually is. Okay, so let's actually look at that particular, and if we get that, we can look at how this gets applied to this, and we end up with lambda x, expressive x, and restaurant x. These x's are different. Remember, the x's are all conditioned on the particular lambda. Okay. Likewise with Noah, Noah just gets copied up. What about that VP rule? The VP goes to VBZ to NP, and what we just say, well, we're going to apply whatever the semantics of the VBZ is to the semantics of what the NP is. So the semantics of the VBZ is this complex lambda form here. Notice that it's lambda f is the top one, so effectively that f is going to get this lambda value, which we're then going to reduce to lambda y, lambda x, and that f in there is going to be replaced with all of that expression, okay? And then we end up with something like this, okay? Then, okay, what we want to know is S goes to NP-VP, okay? And what we say is, well, S goes to NP-VP, it's the semantics of the VP applied to the semantics of the NP, okay? And that's going to be this whole expression here being applied to Noah, okay? So lambda y is going to get applied, and so all occurrences of y is going to get replaced with Noah, and so we end up with we end up with the answer that we actually want, which is for all x expensive x, restaurant X likes Noah X. Okay. Now, that might have been faster than what you wanted to be. There are multiple lambda reductions going on there, and you have to do it. And believe me, it does work, because I thought there was a bug in these slides a couple of times ago, and it's not. It's actually right. But following it through actually gives you the right answer. But it does mean that we have to have all these syntactic rules with a definition of what the form is, and we have to give a definition of what the lexical entries, the things at the bottom end are, if this is going to work. Okay. Life's a little harder than that, because life's always a little harder than the first example that you see. And I'm going to talk about something else that happens in first order predicate logic, a thing called quantifier scope ambiguity. Even though you've got all this logic form, actually you can discover that there's multiple meanings to a sentence that are not immediately obvious, at least given one particular surface form, and it can be quite hard to find out how to represent those in first order predicate logic. Actually, it's relatively easy, but there are two meanings. So if we think about this statement, and this is the famous statement, it always gets used, and therefore that's why I'm showing it. It's not for some other reason. It's because if you search for every man loves a woman, you'll find explanations about this. It's probably got its own Wikipedia entry. Every man loves a woman is ambiguous, okay? And the question is, how many women are we talking about? Is it for each man, there's a woman, but not necessarily the same woman that the man loves, or is there one woman and only one woman that every single man loves that and only, well, maybe not only, but loves that woman, okay? Now, that difference, okay, if a broad scope for a woman or a single case for a woman, actually can be represented first order predicate logic pretty easily, okay? And so one we can say as, for all you, man you implies that exists woman X and loves UX. And this is the case where if each man loves a different woman, this is true, okay? And they could still love sometimes the same woman. Well, the second one is you move this exists X out to the front and you say there exists a woman. So you make the particular pick about the woman, and then you say every man actually loves that particular pick of the woman. And this is what's called quantifier scope, and it's ambiguous in the language. It's like deeply, fundamentally ambiguous. Many people don't see that, although occasionally people will make jokes about it. You know, did you know that in every 5 minutes a man is knocked down by a car? And he's getting really pissed off about it, okay? So that joke, sorry for the example of the joke, but it's appropriate to what we're talking about, is that you expect every 5 minutes a man gets knocked down by a car. You expect it to be not a particular man. You expect it to be some different person, all over the country randomly being knocked down by a car. But when I say, and he's getting really pissed off about it, I've changed the meaning to mean there is this guy who's called Fred, and every time he steps out in the streets, he gets knocked over, okay? Poor guy, okay? And that's the contrast between these two ambiguities, okay? And be aware, life's a little even harder than that. So if I say a statement like a seat was available for every customer, there are 100 customers, how many seats are there? Probably 100, or there's going to be some pretty pissed off customers, okay? However, if I say a toll-free number was available for every customer, I've got almost the same syntax. All I've done is replace seat with toll-free number. How many toll-free numbers are available when there's 100 customers? The answer is 1, probably, maybe 2, but 1, okay? And so these two statements, you have got a different reading of those based on your world knowledge. And then if I say something like a secretary phoned up each director, okay, it doesn't have to be even a different secretary for each director or one secretary called them all. It's just we have some secretaries, we have some directors. They called until everybody, all the directors were called. So there's actually other interpretations too. Likewise, a letter was sent to every customer, okay? I think you'd be pretty pissed off if you received a letter from your electricity company and at the end of it, it said, please pass this letter on to your neighbor. What? Okay, because that letter is being passed on to every customer. So you have to go next door and give it to them. That's not what it means, probably, okay? So all of these have sort of got an understood reading or an underspecified reading. And in first order predicate logic, we sort of have to care about it. There was a bunch of work way back in the 90s, might have been even in the 80s, but I think it was the 90s, on translation. And the question is, if you're trying to get a logical representation of the sentence that you're translating, do you need to resolve the ambiguity? And it was noted by a bunch of people, somewhat famously, who were actually working on most of Northern European languages. They were in Sweden, Swedish, Norwegian, Danish, German, and English. They noticed that these ambiguities are exactly the same across these languages. The same ambiguities are there. And so they worked out, you actually don't need to resolve them. And so they came up with non-resolved logical forms that would allow them to be able to translate things. And it was sort of a big thing at the time, as saying some of these ambiguities are not important and therefore you don't have to care about it. However, okay, for those of you who speak non-European languages, okay, I want you to think about a seat was available for every customer and the toll-free number was available for every customer. And if you're not old enough to know what a toll-free number actually is, think about a website. A website was available for every customer, or an email address was available for every customer. Well, that really is genuinely, is it for complaining or is it for their own email? Think about this and translate it into Chinese or Hindi or whatever other language you say, and think about whether that ambiguity is there or not. For the most part, you'll find you have to change the syntax quite distinctly to be able to describe these two meanings. And it's pretty hard to come up with a single sentence that covers both of these meanings, okay? So think about that. So it depends on the language, okay? But there'll be other problems in other languages for time. Remember in the syntax form, when I was talking about other interesting parsing techniques, I told you that there was a thing called combinatorial categorical grammar, CCG, about how cool it was from a syntactic point of view, because it has 5 and only 5 rules, and it covers everything in English. In fact, everything in every language. I think everything in every language, but definitely everything in English and probably most languages. So it only has 5 grammar rules, okay, which is pretty cool. But the cost of doing this is that you make the lexical entries much more complex. So in a more standard context-free grammar, what you have is you just have part of speech tags at the bottom, but here you end up with these complex things that are saying things like S/NP at the bottom. Now, it happens that categorical grammar not only has got 5 simple syntactic rules, but in fact, the semantics of them are just as simple. They also only have 5, the same 5, and we can actually do semantics and end up with the first order predicate logic representations out of these rules. And that's sort of one of the other things that makes CCG so interesting, because what it's done is it's got rid of a lot of the complexity in these rules. Remember, we were talking about rules and what the semantic rule was going to be for this syntactic rule. And at the moment, a human has to go in and go, I think you do this, and oh yeah, that works out. Or, oh no, that doesn't, I have to change it. Oh, I'm going to have 2 rules for this. But no, for categorical grammar, we can get away with 5. That's just cool. So let's have a look at this. Okay, so this is the syntactic one. So we have John, Mary, likes. Likes is this thing with brackets. And what the slash basically says is, I'm looking for. And a backslash means I'm looking for something before me. And the forward slash means I'm looking for something after me. So how to read the likes form is saying, likes is a thing that if it gets an NP to the right of it, it forms something that if I get an NP to the left of it, I get a sentence, okay? So let's have a look at this. We have John likes Mary. We put in their lexical forms. We apply forward application. So we have likes has an NP after it. So this gives us an S/NP. So we're effectively canceling out that NP. And then we're looking for an NP before us. So we do have an NP before us, and that gives us S. Okay, this is syntactic parsing. Okay. Likewise, we can do this with more complex forms. But what about the semantics? Well, the semantics is almost as simple, especially as we're using lambda calculus. Okay, and so if we're just going to look at John walks, we still are just going to use backward application. And so what we're saying is, when we're doing that, the semantics, in this case forward application, plus something that's got some other semantics after the colon, we just actually apply, lambda apply S to T, and then do lambda reduction on it. Okay, so if NP is J, so and the semantics is J, and the semantics of walks is X /NP, and the semantics is lambda X walks X. Okay, all we have to do to get John's walks is we basically are applying lambda X walks X to J and then do the reduction. So we're only doing here where what we're doing is we're taking whatever the T is, this is looking forward rather than back, and it gives you the answer. Okay, so here's the step-by-step. This is the / form where we actually get its representation. And what we then do is we say, okay, we're going to date the NP J plus S /NP and lambda X walks X. So the semantics is going to be lambda X walks X dot applied to J, and this reduces to walks J. This is a very simple example, and of course this is going to work because I'm biased on this. I actually think CCG is pretty interesting. Okay, here's a more complex one. Okay, you can go through it. It's just as easy. Basically, it's always the same thing. In fact, that slash is telling you the backslash is telling you the order of who applies to what, the X to Y. Okay, which is going to be the left-hand side and which is going to be the right-hand side of the dot application function, and we end up with the same thing. And this works for much more complex things. So it works for all of our examples of all of our examples of implication type things. It just works. Okay, and it's pretty neat. It does mean that you have to work out what the lexical entries have to be, and that could be hard. Okay, however, along comes probabilistic techniques learned from data. We can derive the lexical entries from data-ish. So what we can do is we can say, here's a constraint of what these entries might look like. Okay, so there's not an infinite number of possible entries. There's actually a finite number, and you can talk about them in terms of a tree. And so what you can do is you can assign all possible values to a word, and you can see which ones actually parse. Okay, and if you have training data, you can see which ones parse and give you the right semantic answer. So now what you can do is you can say, well, I can try all of these different values for the lexical entries automatically and find out which ones work. And if they work, I'm going to increase the probability of it being that, and I'm going to decrease the probability of the ones that didn't work. And I'm going to try the next sentence, I'm going to try the next sentence, I'm going to try the next sentence. And then I'm going to get weights over all of the potential lexical entries given a particular word. Now, actually, you have to do things a little bit more than that because there's a lot of entries, okay? And there potentially could be funny ambiguities. And there's a rule at the end that's called type raising, which is best described as utter magic. If you understand what lambda calculus is and you understand about curried functions, you know exactly what that's doing. And you've got to be sparingly with that. Otherwise, things disappear into never ending. But there's constraints, reasonable constraints you can put on it, and you can find pretty good examples of representations for CCGs. Now, it still only really works for nice literal things, okay? You're not going to be able to stuff arbitrary philosophy down there and say, look, it understands it, because it's not. But for things like Wikipedia entries that actually have real facts in them, it can work pretty well. And so people are doing this. And so both probabilistic CCGs and nowadays people, because there's now training sets that have already discovered this for, yes, you've guessed it, the Penn Tree Bank, because that's what NLP people actually do, end up with a representation for everything in the Wall Street Journal in 1992. And we've used that to be able to build computational neural systems that use CCGs. Okay. Now, we still have to be a little careful about this. We've not solved everything in computational semantics, but this sort of works for things where there's very concrete facts in there. So first paragraph of Wikipedia articles are a pretty good example. First paragraph of Wikipedia articles that have got that style, which includes most cities, countries, movies, people, etc. CCG is by far not the only one, okay? And it might actually be too general for some of the things we want to do. Dipanjan Das, who's now a senior manager at Google for his PhD while he was at CMU, built this system called Semaphore. He used FrameNet. We talked about FrameNet before. FrameNet gives us verbs and what the arguments to the verbs actually are. So it sort of predefines what the verbs in the arguments. So using that, he actually tried to build automatically or probabilistically build a syntactic parser that could give you frames from FramesNet as the answer. And frames from FrameNet are effectively a meaning representation language. They're a simplified form of first order predicate logic, but they're a very useful one because they're giving you the arguments and of the verbs. And for the verbs that are in FrameNet, you can actually get something that's quite good. I also, no, I didn't mention this because it was in another class that I was talking about. Vivian Chen, who was a PhD student here after Dipanjan, she's now a professor at National Taiwan University. What she did was look at, could she actually extend Semaphore by automatically trying to find these frames in data, particularly for dialogue systems. So when you've got a new domain, you've got a bunch of data that's talking about restaurants. Can you actually extract from there and make the frames that are appropriate for the domain that you're actually in, even if they weren't originally in FrameNet, to be able to add to them and then give a semantic output for it. There are other semantic parsers out there. It's quite a thing to try to do. They're usually particularly targeted on domains because that's what people want. Everybody says, I want a generalized one, but nobody wants a generalized one. Not if they want to use it anyway. They actually want it for a particular domain, okay? There's things out there that will try to find events and entities. Events are a little harder than actually just simple facts. Semantic role labeling that we also mentioned about in the last lecture is a sort of semantics, and often it's a sufficient semantics to allow us to do some of our downstream tasks, particularly neural identification, particularly things like summarization, particular things like some information extraction things can be done with just semantic role labeling, or things that don't have anything like that get better with semantic role labeling. They probably would get even better if you could get semantics, but it's sort of hard to get good semantics, and it's really hard to measure whether you've got the right semantics. So evaluation is particularly hard. I already mentioned that in things like Amazon Alexa and Siri, they often call these things intents and slots. So people have tried to do this from data and try to discover data, and they can do fairly well, especially in targeted domains. They can do quite well, and they can even identify the ones that I'm not sure about, but I think it might be this. And therefore, you know, in a dialogue system, you can say, did you mean that I have to set an alarm for 2 a.m. tomorrow morning, or did you mean something else? Some things can get away with not doing semantics at all, because actually a bag of words does surprisingly well for an awful lot of tasks, okay? And we always like to think that detailed semantic interpretation was really what we ultimately want to do. But although lots of people who've worked in semantics would love that to be the case, that you really need to get, you know, the real meaning out of it, actually an awful lot of natural language tasks do not require that. So don't get pulled into doing semantics when you actually maybe don't need it. But it's worth knowing it's there. It's worth knowing that for particular tasks, it can help, but try to understand that they really have to be particular types of tasks, and they really have to have pretty well-defined semantics before you're going to be good enough when you extract the information that it'll be reliable enough for your downstream task to actually make it. We'd like to find the canonical meaning from sentences. That's like fundamental. And that's really what we're doing in all of these. There's just random stuff that people say and they all mean the same thing. There's just 1,000 different ways of ordering pizza. And all we actually want is, you know, to call the Python function that says order pizza and list the toppings that are to be on it, and that's it. And we don't really care how they said it. We don't really care how polite or impolite they said it. We don't care how broken English they said it. We just want the information out so we can execute what the person actually wanted, execute that command to be able to do what it actually is. And that's what we're really trying to do. And if that's our goal, we don't always need the right semantics. We just need to give the right semantics for our downstream task. And so that's important to actually remember. Okay, that is it for today. Are there any questions?